So yeah, thank you everyone for being here. I guess before we jump into the exciting stuff, let's just make sure we all agree what pi is. So, all right, I hope you're not insulted. Let's just go back to the beginning from, thousands of years ago. We start with a circle and say that the distance around the circle, that's the circumference. The distance through the center of the circle, that's the diameter. And pi is just whatever number you get if you take the circumference, you take the distance around, and you divide it by the diameter. That's what we call pi. And it happens to be the case if you measured real circles in real life, you would get something a little bit more than three. We know that the decimal expansion goes on forever, but it most students end up kind of lodging in their brain somewhere that pi is about 3.14, which is why we celebrate Pi Day on March 14th. I guess our approximation of pi being 3.12 today is, well, okay, it's not ideal, but it's not the worst. It's certainly not the worst approximation of pi I'm going to give you today. um, and maybe I'll say that actually, in order to make some of the results today pop, let's lodge into our brains a couple more decimal places. So actually, let's try to remember that pi is the up to, I guess, 5 decimal places, 3.1415. Uh, okay. And I guess one other thing I want to get into before jumping into the really exciting stuff is, oh, I don't want to call these unexciting occurrences of pi, but I guess I want to say there are some occurrences of pi that don't happen with just a circle where it shows up and we're not that surprised. Because it shows up in kind of lots of circle-ish things, like the cylinder or a cone with a circular base or a sphere. Pi shows up in the volumes of all of these objects. And I just want to let you know, this is not what I am talking about when I talk about pi without circles. All right, we see circles all around here. That's not what I'm talking about. I'm talking about wild examples of pi. All right, let's get into it. All right, this is the first example that I ever saw where pi came out completely surprisingly. And I think it was my dad who showed me when I was a young girl. And it's wild. So it is called the Buffon needle experiment. And let me tell you a little bit about it. So in the late 1800s, a French mathematician, Comte de Buffon, legend has it he was walking on a hardwood floor and had a needle in his hand and dropped it on the hardwood floor. And when he dropped it, where it landed crossing the line between two slats on the hardwood floor. And being a mathematician, he thought, oh, I wonder what the probability is that dropping that needle made it land so that it crossed between two slats, as opposed to, say, falling entirely within a slat and not crossing. And also, being a mathematician, he solved that problem and almost immediately realized he had a probabilistic way of determining pi. So let's see it. All right, so these blue lines, let's just imagine that those are what are representing the lines between slats. And here's our probabilistic method for determining pi. You take a bunch of needles and you just throw them on the slats. And okay, assuming that the distance between the slats is about the same width as the needles, turns out pi is about 2 times the number of sticks you threw divided by the number of sticks that crossed one of the lines. What? Yeah. You can approximate pi by taking a handful of sticks that are straight, throwing them on a bunch of straight lines, counting, and that gives you an approximation of pi. And the more sticks you throw, the better approximation you get. In this example, let's see, we've thrown 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 sticks. And We'll count the number of crossings. By crossings, I mean sticks that cross one of the lines. So that's 1, 2, 3, 4, 5, 6 crossings. So in this highly, you should be suspicious, right? Because I'm setting this up. But in this example, we say, all right, 2 times the number of sticks that I threw, which is 10. That gives us 20, divided by the number of sticks with crossings, that's 6. That gives us 3.333333 approximation of pi, which is within 10% of the actual value of pi. And that's not bad for just throwing 10 sticks and counting. But I hope you're just all very suspicious and won't take me for my word. And so I'm actually going to do this experiment in real time. So I'm going to stop sharing my screen for a moment. And so hopefully you have it on speaker view or have me pinned. But I've got we're going to do some Buffon needle experiment tests right now. And hopefully, guys, let's hope I toss these really randomly and that we get a great approximation of pi. I've done this before and gotten terrible approximations, like 6 or something, I think was the worst approximation I got. So, all right, here are my, I've got toothpicks. These toothpicks are about the width of the lines between the slats. And I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 toothpicks. Okay, wish me luck that I actually distribute these randomly. Okay, let's see. All right, let's count the number of crossings. 1, 2, 3, 4, 5, 6. Oh, this isn't going to be amazing. It'll be okay though. It's going to be all right. It's going to be all right. All right, let's see. So I threw 11. So 2 times 11 divided by 6 gives us 3.67. Okay, so that's 20% error. But all right, I'm hopeful for better. I think if I don't get better in 3 throws, we'll move on with our lives. But okay, let's try. Wish me luck. Oh no. Oh no, I dropped one. Okay, all right. Let's see. 1, 2, 3, 4, 5. Oh God, these are like all crossing. This is going to be terrible. All right, so I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 crossing. Yikes. Yeah, that's going to be 2.2. All right, so we're getting worse. I know I said only one more, but if I get a terrible approximation of pi again, I'm probably going to do it again. All right. The rest of the talk is just me trying to get better than a 10% error. But, we have an hour, so that's good. All right. Whoops. Ugh. All right, let's see. 1, 2, 3, 4, 5, 6, 7 crossings. All right. Let's see what we get when we do 7 crossings. That's 2 times 11 divided by 7. That's 3.143. Hey, look at that. So with only some minor fudging, all right, we got to, we got the first 3 digits of pi. All right. Forgive me for that fudge factor. Sorry, everybody. I didn't have the strength of will to continue until I actually got it naturally. All right. Back to the slides. Okay. Oh, let's try it. I guess I should have moved one more slide. All right. But here's a question. Where is the circle exactly? I mean, like I said, we're throwing straight sticks onto straight lines and counting. But actually, there is a circle hiding in the background that kind of explains why pi might show up. I'm wondering if we have any brave souls who want to hazard a guess. You're like, not since this is being recorded. All right. I'll give 4 seconds for somebody to take one for the team. Oh, maybe somebody's putting something in the chat. Ah, yes. Okay. All right. We got a couple of good answers in the chat. So, yeah, the chat consensus is the rotation of the sticks. And indeed, that is correct. So let's return to the slats. Let's return to our needle that was dropped and crossed a slat. Now, whether your needle that's dropped crosses the slat or not depends on 2 things. First, it depends on, in some sense, how close your needle is to the slats. So like if you looked at the center of your needle, how close the center lies to one of the edges. All right, the closer your center is, the more likely you are to cross. And then the other thing that it depends on is, all right, well, no matter how close your center is, it depends on how your circle is or how your stick is rotated. And so it depends on where along this circle the rotation lies. So if it's here, you don't get a crossing, but here you do. And so really the way to sort of see why pi is coming up is you can think of it as like you're throwing a bunch of little diameters onto the slats. And that's really where pi is showing up. All right, guys, I got it. This is just a hit parade. So here's another great one. Oh yeah, another experiment. Okay. Let's do, all right, I'm gonna stop sharing again. We're gonna put this back here, and I've got now this strange device which my father-in-law made. Thank you, Dave Hagen. And what I'm going to do is, this device is just a piece of wood with 2 tracks screwed onto it so that it can just keep these, the balls that I'm rolling, keep them in line. And so here's what I'm going to do. I'm just going to take one ping pong, these are just ping pong balls. I'm going to take one and just bash it into the other. And what I'm interested in is how many collisions do we get? So I bash it in. I got 1, 2, 3 collisions. And that makes sense. That's not suspicious. I mean, 3, I guess, is close to pi, but this is such an innocent thing to do. That certainly has nothing to do with pi, right? Certainly not. But okay, so that's what I'm interested in. And maybe it's not an interesting question. Maybe we could have thought our way through it if the balls are the same size, because okay, it's just your momentum's going to travel. And like this ball's going to stop, this one's going to hit there, come back. That's, in an ideal sense, that's all that's going to happen. Of course, you're going to get 3 collisions. But what about if I have a slightly, or not even just slightly, a heavier ball? So this is a this is a golf ball, not a ping pong ball. And so now I'm interested, all right, well, now how many collisions am I going to get? Because now when my golf ball hits the ping pong ball, sure, the ping pong ball will shoot off, but this is going to keep rolling, and there's going to be some like bouncing back and forth until it stops. And so I'm going to need a volunteer. Anybody here good at counting? I know I have some seniors here. Who's good at counting?
I can count for you.
Thank you, Catherine. I truly appreciate it. All right, so here's what you're going to do, Catherine. I am going to do this like bashing one ball into the other, and you're going to just try your best to count the number of collisions that happen. And okay. I'll go slow, okay?
Okay.
All right. Are you paying close attention?
Yes.
Okay. I'm sorry. I was just trolling you. There's no way you could count that. Sorry, everybody.
Okay. I was about to say, I have no idea.
I couldn't resist. Yeah. All right. Thank you. A round of applause for Catherine for being a great sport about that. I like how all my students were like, I knew it. I knew it. She had something up her sleeve. Okay, let me go back to sharing my screen. All right, so we did our experiment. Uh, let's, all right, think just theoretically, what should we be getting? Now, before you think, I know where pi came in, it's because you were throwing spheres around. No. Well, I mean, we haven't seen pi yet, but I know you're thinking, you're like, I'm seeing what the magician's doing. Nothing to do with the fact that I was rolling a ball. In fact, let's think no circles at all. Let's think sliding blocks, where, okay, maybe we have two blocks that are the exact same size. And let's suppose that this like plane that they're sliding on is frictionless. Like, imagine square hockey pucks bouncing around on an ice rink. Then, okay, it's same as with the spheres. You're gonna have a situation where one block slams into another, one collision, shoots off a block that slams into the wall, a second collision, comes back, collides with the original block shoots off. Okay, so let's keep track of some data. So, all right, if the two blocks are the same size, then the number of collisions is 3. But what about if the block you're smashing into it, what if that's 100 times as big as the smaller block? Then how many collisions should you get? Turns out this can be calculated exactly, and the exact number of collisions you get is 31. What if it was like 10,000 times as big? All right, maybe you don't have, you need a super, super high-speed camera to track this. But if it was 10,000 times as big as that first one, all right, this is not to scale, you get exactly 314 collisions. And I hope your heart is racing right now. What about 1,000,000 times? What if that first block was 1,000,000 times the size of the smaller block? Anyone want to hazard a guess as to how many collisions exactly there would be?
You have some good guesses in the chat.
Oh man, I haven't even been monitoring the chat.
Oh, it's wild.
Okay. Oh, good.
Our math majors are showing up. Thanks, guys.
Good. I see some right answers in there. Exactly 3,141. Yeah. So if you put the decimal point in the right place and you increase the size difference by 2 orders of magnitude, you get exactly an extra the next digit of pi. Whoa, this blew my mind, because especially this, like with the first one where they're the same and you get 3 collisions, it's so innocent. You would never suspect. All right, so where's the circle? Don't worry, I'm not going to make you hazard any guesses. I would never have guessed this. Okay, warning. For those of you who hate equations and were led here under false pretenses about what kind of math talk this would be, there are going to be a few equations coming up. So, all right, if you're not cool with that, go ahead and check TikTok or something for the moment. But if you're okay with equations, I think it's worth paying attention. We're going to talk about the equation that gives you a circle in the plane. So, okay, draw a circle in the plane, take a point on that circle, call it xy. That's just, the x represents your horizontal distance, and the y represents your vertical distance. And then, okay, if you drew a line between the center of the circle and the point, that line actually represents the radius of it represents the radius of the circle, but also the hypotenuse of a right triangle. And Pythagoras' theorem tells us this is if you have a right triangle, a squared plus b squared equals c squared, where c is the hypotenuse. And so the Pythagorean theorem tells us that if we have a circle, any point on the circle can be described by x squared plus y squared is the radius squared. Which, okay, we'll just make slightly more general and say, okay, the equation of a circle then just is x squared plus y squared equals some constant. If that constant is 4, it's a circle of radius 2. But it's just x squared plus y squared is constant. That is the equation of a circle. Okay, so let's talk about our system here. We've got two blocks. They're different masses. They're traveling at different velocities. And maybe you remember from physics, or maybe this is news to you, but the kinetic energy of a moving object is 1/2 times the mass of the object times the velocity squared. And so in this situation, all right, the kinetic energy of this first block is 1/2 m1 times v1 squared. All right, the kinetic energy of the second block is 1/2 m2 v2 squared. But here's the kicker. The conservation of energy tells us that the sum of the kinetic energies must be constant. So we get this equation. 1/2 m1 v1 squared plus 1/2 m2 v2 squared is a constant. And if you'll allow me to do a little change of variables, if you think of x as being the square root of this first term and y being the square root of this second term, then we really do have the equation of a circle, or okay, a sphere for all of the, mathematicians who are like skin is crawling right now. But you really do get this equation from the conservation of energy of two objects in this closed system. Now, how this actually means counting collisions spits out the digits of pi, okay, that is too complicated to get into. But this really is where pi shows up. It shows up because the conservation of energy gives you the equation of a circle. All right, that was cool. You have to admit that was cool. Here's another wild one. Okay, so suppose you have an even number of coins. You throw them in the air, they land. Natural thing to ask is, all right, what's the chance that you get the same number of heads as tails? Well, I don't know. Probabilities is hard. Just look at a simple example. Let's look at the simplest example. Let's just throw 2 coins. What are even the options? All right, well, if we throw 2 coins, we could get 2 heads. We could get heads, tails. We could get tails, heads. And we could get tails, tails. So those are our 4 options. And of these 4 options, it looks like 2 of them have the same number of heads as tails. So the chance of getting the same number of heads as tails is 2/4, or okay, 1/2. And don't worry, I'm not trying to sit here and convince you that 1/2 is a great approximation of pi. This has nothing to do with pi so far, so far as we can tell. But let's get some more data. Let's try throwing 4 coins. We could get 4 heads. We could get heads, 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 tails. We could get heads, heads, tails, heads. I'm not going to say all 16 possibilities. I'll just put them here, and hopefully you can come back later and check my slides that I have them all. But okay, when you come back and check these slides, you say, oh yeah, those are all the possibilities. There are 16. And these 6 possibilities are such that they're the same number of heads as tails. It's okay, if we're tossing 4 coins, the probability that you get the same number of heads as tails is now going to be 6/16, which, all right, if you are so compelled, you can reduce that to 3/8, which is less than 1/2. So we're getting farther from pi, so this is worse. All right, let's get some more data. I'm actually going to plot these points. So my x-axis here is going to be the number of coins I'm throwing, and the y-axis is going to be the probability. So if I throw 2 coins, the probability is 1/2. If I throw 4 coins, the probability is 3/8. For 6, 8, and 10 coins, we get probabilities that look like this. And that actually seems like maybe there's a pattern happening. Let's look at a couple more points. Okay, this definitely seems like there is a graph that, like, we should be able to come up with a function that models this. Oh my God. Yeah. Turns out these probabilities approach the equation of the line y equals square root of 2 over pi times x, where x is the number of coins you threw. And this isn't a trick. It's not like I just fiddled with things. It really does approach it, and it approaches it like that. Yeah. All right. Where's the circle? I know what you're thinking. You threw circular coins. I see what you're doing. Nothing to do with the fact that the coins were circles, guys. This works the same if you had square coins. Because really, what we're counting is the possibility or the probability of getting the same number of heads as tails. So, I mean, you could have taken a deck of cards, thrown them in the air, and counted how many were face up versus face down and asked what's the probability of getting the same number face up as face down. It truly has nothing to do with the fact that I was using pennies, which happen to be circular. So where is the circle? Don't ask. It's there, but don't ask. Okay, fine. Like, there is something there. I read some research paper. Some mathematician very cleverly realized you could organize the probabilities as rectangles and stack them in a way such that you do start to see a circle coming out of it. And I am not going to give you any deeper of an explanation than that. Oh, guys, this one's my favorite. This is also, fair warning, the one that is going to take the most time to set up. Indeed, I was told, if you're running short on time, you might cut the fractals one because it's only one example and it takes up so much time. And I was like, but it's my favorite. So we're going to do this. And if we're running short on time, we're just going to lightning round everything after it. So let's do it. Okay, we're going to be talking about the Mandelbrot set, everyone's favorite fractal. And again, before you start feeling smug and you're like, I know where the circles are. They're right here and right here and right here and here and here. Yeah, there are totally an infinite number of circles, and I'm not talking about any of them. But I guess in order to see the like crazy way that pi shows up here, I need to explain what the Mandelbrot set is. Like, where does a picture like this even come from? Now, a side note to the mathematicians in the audience. I am not going to mention imaginary numbers. And you are going to need to be chill about this. Okay. All right. So, mathematicians don't have enough hobbies and periodically like to do things like draw little arrow buddies on a graph. We call these little arrow buddies vectors because little arrow buddies, adorable as it is, somehow has not caught on, and maybe because it takes too much time. So, okay, and not satisfied with just drawing one, sometimes we'll draw a second one on our graph, but always coming out of the origin. And it turns out that mathematicians have come up with a way to, what we say, add these vectors together. And what we mean by adding vectors is we stack one of the vectors on top of the other one. So, like, move it up like that. And then just draw a new line starting from the origin to the tip of the stacked vector. And you get a new vector. Okay. So we've just added two vectors. And don't worry, you are not going to need to remember how to add vectors. You're not going to be tested on that. Only the students who showed up today are going to have homework problems on it. Just kidding. So yeah, don't worry about it. This is just really to give you an idea that mathematicians have made sense of this idea of adding vectors. And not just adding, actually. We can also talk about multiplying vectors. How do we multiply two vectors? Well, first we look at the angle between the vectors, the angle that they make with the x-axis. So, all right, I'll call this first angle theta 1 and the second angle theta 2. But the point is, I take these angles that the vectors make with the x-axis, and the first thing I do is I add them together. Okay, so now this new angle is the two angles added together. And then I take the lengths of each of these vectors. You know, you can just measure them, take their lengths, and multiply the lengths together. And create a vector that has the angle from the x-axis of theta 1 plus theta 2, but the length where the two lengths that you get from multiplying the two lengths together. And you get a new vector. And this new vector is what we say as what you got from multiplying those first two vectors. Again, you're not going to need to remember how to do this. This is just to give you a sense that it's meaningful to say multiply and add vectors. All right, you've been very patient. Seriously though, where does this come from? Well, it's a process. First, pick a vector. Okay, so I've got my little arrow buddy. It's my special one. I've picked it. Now in the process, multiply it by itself. So like pretend I have two arrows here and multiply them together. Get something like that. Now I'll add this new vector, add it to my original one. So I stack it. I get this new vector. And I enjoy that new vector that I have produced. And then I repeat. And not just with any old vector, I repeat with this blue vector now. So now this is the vector that I multiply by itself. I add it to my original vector, so my special little arrow buddy from the beginning, and enjoy the new vector that I get. And then I repeat and repeat and repeat and repeat. And mathematicians like to ask, okay, well, what happens if you keep repeating this process? And it seems like, at least in this example, okay, these are just going to be getting bigger and bigger, these arrows. Just the lengths are getting larger and larger, and that's right. But it turns out that if you choose your initial vector small enough, you just keep going around maybe in a cycle, or at the very least, no matter how many times you repeat the process, it stays bounded. Like actually, it'll stay within a circle of radius too. So here's where the Mandelbrot set comes from. This fractal, all of the black parts in this image are vectors where if you drew a vector to these points and you repeated the process as many times as you wanted, you never leave a circle of radius 2. So that's where it comes from. Those are all the black parts. Everything else that has color, those are vectors where if you repeat the process enough time, you're going to jump out of a circle of radius 2. And the color represents how fast you jump out of that circle of radius 2. So that's where the color comes from. Okay, but you were here for the pie. So where's the pie coming in? Well, okay, let's just focus in on this part on the x-axis. And it turns out that this point right here, this very last point that stays within the Mandelbrot set, so it's the last black dot on the x-axis, that is at exactly 1/4, or 0.25. But let's look at some point kind of farther along the x-axis, like maybe here. You can totally ask, well, how many steps would it take this point to get larger than 2? I mean, we can ask that of any. 2 happens to be the special number here. But all right, we could ask it about this point or this point. And in fact, you could say, all right, well, let's take points closer and closer to this 0.25. Let's just get closer and closer and keep track of how many steps it takes and see if we find a pattern. So, okay, let's do it. Let's keep track in a table. So let's say we're pretty close, like really close to 0.025. We only go 0.01 distance to the right on the x-axis. So our starting value is 0.26. How many steps does it take to, how many times in that do you have to repeat the process to jump greater than 2? 30. Okay. What if you're 0.0001, like super close? So your starting value is like 0.2501. How many steps does it take? 312. Okay, all right. Let's get like absurdly close, like super close. So our starting value is 0.250001. The number of steps is 3,140. Again, I hope your hearts are starting to race. We got really, really, really close. Just so close. We get 31,414. Okay, so these last digits are garbage, but each jump closer, we're getting an extra digit of pi, correct, if we put the decimal point in the right place. In fact, I'm under the impression that this is actually how this was discovered. Was somebody was actually counting steps and just got closer and closer by an order of magnitude and saw the pattern. And I swear that if that was me, my mind would have broken. I don't think I could have recovered if I had accidentally found pi this way. It was my favorite. It was like, I found, seeing this, I was like, I want to give a talk about crazy places where you find pi. So where is the circle here? Like, okay, we're taking a vector, we're multiplying it by itself, we're adding and we're repeating the process. Where is the circle? I have no idea. I don't know, man. I've read some papers that have convinced me that yes, it really is pi, but I don't see any way where introducing a circle into the situation is enlightening. And in fact, it kind of has gotten me thinking, does there need to always be a circle in the background? So is it the case that if we see pi popping up in some physics or chemistry or some natural science or in mathematics in some unexpected way, did we need to have pi show up? Or sorry, did we need to have a circle show up? Like, is there always a circle hiding in the background? Or could it really be that you could see the digits of pi popping up in some iterated process and that it truly has nothing to do with circles? I mean, in one sense, pi is just a number, a little bit more than 3. Does it always need to be tied to a circle? I want you to think about this a little bit. So I'm actually going to, surprise, throw you in breakout rooms and have you discuss for exactly 5 minutes. I know for a fact that there's a philosophy professor in the audience today. So, hope you, I was going to say, do you hope you get that guy in your room or do you hope you don't get that guy in your room? But in any case, sorry, Ryan Hickerson. Yeah, I'm going to throw you into breakout rooms. I'm going to put, 4 or 5 people in the room, each room, and I'm going to give you exactly 5 minutes to talk about it. So, be efficient with your time. Say, hey, this is my name. I had no idea this was happening. I'm really nervous about this. But also, here's my extremely strong opinion about whether there is a circle in the background or not. Okay, let me open up the breakout rooms. How many people do we have? 70! My word. I guess I need more than 8. Yeah, okay. All right, I hope you'll join your rooms. I can only assume that it would have come to blows if we were all in person. So probably good that it was all over Zoom. Okay, for my own, I guess I'll give my own opinion. Do I think there always has to be a circle hiding in the background? I think no. But also, I don't think that this is a question mathematicians can answer. I think this is a philosophical question. And I guess, so here's maybe I'll give one reason for why I don't think a circle always has to be hiding in the background. Or at least it's maybe not always illuminating to find the circle. Is because I think we could have just as easily defined pi to be the number that you get when you take the Mandelbrot set, you approach 0.25 along the real axis, and you count how many steps you need to jump past 2. Like, you could define pi that way. It's the number that those digits approach. In which case, if you had defined pi that way, you'd be asking, when you take the circumference of a circle divided by the diameter, I wonder if there's a Mandelbrot set hiding in the background. And that seems not right to me. But I don't see, I see why historically we have defined pi in terms of circles, and I see totally why humans are biased towards circles and seeing pi there. But I don't think, like, on a philosophical level, I don't think it needed to be that way. So, okay, I've tipped my hand, and I'd be happy to hear all of your objections to that at the end of the talk. Let's get through a few more examples. Okay, I have 10 minutes. Let's see how many we can get through. Okay, factorials. This is also wild. So factorials, maybe this is a reminder for you, maybe you've never heard of them before, but I'll just say the process first and then do an example, and it's way better than just seeing the formal equation written out. Factorials is what happens when you take a whole number and you multiply it by every number less than it, going all the way down to 1. So, okay, something like 4 factorial. And mathematicians are so precious. We write factorial with an exclamation mark. 4 factorial is just 4 times 3 times 2 times 1. Okay, you take your whole number, exclamation point at the end says that's just that number, times, you just go down the list until you get down to 1, multiply them all together. So 4 times 3 times 2 times 1. All right, 4 times 3 is 12, times 2 is 24, times 1 doesn't change it. So 4 factorial is 24. Why did we bother with the 1? Well, so that 1 factorial makes sense. All right, so then 3 factorial would be 3 times 2 times 1. 3 times 2 is 6, times 1 is 6. 2 factorial, this is getting easier and easier, it's just 2 times 1, which is just 2. And then 1 factorial is, okay, just 1. And all right, this process, or this function, or whatever you want to call it, doesn't come completely out of nowhere. It's used in probability all the time. Like, tons of probability calculations involve this factorials. So, okay, I guess maybe I'll go back and say, all right, I don't see pi here at all, right? This is just, I don't know, 1, 2, 6, 24. But let's graph again those points. So now my x-axis is my starting number, and then the y-axis is the factorial of it. So 1 was 1. Okay, note they're not on the same scale. 2, that was 2. 3 was 6. 4 was 24. And all right, it turns out you could keep going, but the numbers just grow so fast that it's not even worth making a graph of it. But it turns out, in a very mathematically precise way, there is a best line to draw to connect the dots that you get from factorial. All right, this looks good. It's nice and smooth. In one sense, okay, you can draw any lines you want through here, but there is a best one. This is the mathematically best one. And what's interesting about that is you say, okay, well, now I can sort of talk about the factorial, but for not things that aren't whole numbers. So you could do something silly like say, oh, I wonder what 1/2 factorial is. It's the square root of pi over 2. What? What? All we were doing was taking whole numbers and multiplying them by whole numbers less than 1 down to 1. We smoothly connect the dots, and this is exactly square root of pi over 2. And it's not just 1/2. 3/2 factorial, that's 3/4 times the square root of pi. And in fact, any of these halves, you get a square root of pi popping up. Wild. Yeah, and I'm not going to explain why, because in the interest of time, I got a lot more to show you. All right, this is just bonkers, and we really are in lightning round here. So we're going to talk about some infinite sums and some products, infinite products. Okay, so this is a famous problem called the Basel problem. And the problem, besides just having an infinite number of numbers to sum, is figuring out what it is. And so the pattern here is we have in the denominators all right, 1, 2, 3, 4, 5, 6, but they're squared. So we're taking the square numbers, taking their reciprocals, and adding them all up. And you may be worried about adding up an infinite number of things, like doesn't that always equal infinity? But no, actually, it turns out that if you're, you could be adding more and more numbers, but if the numbers you keep adding get small enough and fast enough, you just keep adding more and more, and they actually start to approach a certain number. In this case, it was known for 90 years that this approached a number, but it wasn't known what number that was. And actually, it put mathematician Leonard Euler on the map when he proved that it was exactly pi squared over 6. Let's keep going. How about this? Here's something innocent. Let's just take the odd numbers. All right. Take the reciprocals of odd numbers and alternate adding and subtracting. The odd numbers, just by themselves, have nothing to do with, oh my God, pi over 4. Exactly pi over 4. And actually, my seniors proved both of these things in the last few months, which is kind of exciting. All right, but it's not just addition. There is something called the Wallace product, where, okay, the pattern is we have pairs of even numbers in the numerators, pairs of odd numbers in the denominators, multiply them together, and oh yeah, you get pi over 2. How about something like an infinite fraction? Something that I imagine is a literal nightmare for some math students. A fraction that you could never be done computing. But okay, you get something like this. Again, you're just taking the whole numbers. All right, you're squaring them. You've got odd numbers here. There's a way to define this so that it makes sense. If you keep if you keep going down successively, you get closer and closer to a certain number that is pi over 4 exactly. Why not? Let's take a bunch of square roots of 1/2, where, all right, you get, you're nesting them and you're adding more each time. Don't worry too much about recognizing the pattern. There is one, and it turns out, yeah, oh, that's 2 over pi. Just a bunch of 1/2 square roots that we multiplied together. And then there's my favorite, which is these equations, which are so absurd that they are a product of the human mind, are due to an Indian mathematician, Srinivasa Ramanujan, who was born in the late 1800s, died in the early 1900s. So he came up with these long before computing was a thing. And it's actually somewhat of a mystery how he came up with these incredible formulas. Legend has it he was asked where these came from, and he said that they were given to him in a vision by his family's Hindu goddess. And looking at these and seeing as how there wasn't a proof attached to them, I honestly can't think of a better explanation. It's probably true. Yeah, and here's what else is wild. These formulas for pi that were created over 100 years ago are the basis of some of our fastest ways of approximating pi. Like when computers are calculating the trillionth digit of pi, they are probably using one of these formulas as its base. They converge like that. It's insane. Okay, all right, we're running. We're almost out of time. So I think I will end with what is known as the most beautiful equation in mathematics. And yes, we do have one. It is this, E, which is a number a little bit more than 2.7. I like to tell my students that it's the average of 1 and infinity. And I suppose I shouldn't say that with other mathematicians in the room. But okay, so a number a little bit more than 2.7 raised to the imaginary number I. How do you even do that? Times pi. So pi is also in the exponent. Add 1 to that and you get 0. Thanks, everybody.